5 more problems on Bode plots from control system will be discussed in this video. Now let us start the first problem. So this is the first problem. Here in this figure, the magnitude plot of a transfer function is given, and the shape is like this: one increasing slope. Here it is crossing the 0 dB at 0.5 and slope is 20 dB per decade, and here it is flat 12 dB, and then it is decreasing with the rate minus 40 dB per decade, and again it is crossing 0 dB at omega equal to 8. So this information is provided for this figure. Now we need to find out the transfer function of the system, okay, for this Bode plot. Now this kind of problem I had discussed in the part 1, but here there's little difficulty. That's how I have chosen this problem. Now here this corner frequency, this bending is here. So at which frequency you are having this bending, that is not mentioned. So this corner frequency is not provided. Again, this corner frequency is also not provided. Okay, these are two issues we need to solve it. Otherwise the slopes are given, everything is fine, and we can find out transfer functions. So this corner frequency I'll consider small a, and this corner frequency I'll consider small b. These two we need to find out. Okay. Now let me discuss this function clearly. So as it is having initial slope, so from minus infinity from equal to 0 to up to the a, the slope is plus 20 dB per decade. So as slope is plus 20 dB per decade, obviously it implies that there is 1 0 at origin, that I have discussed in previous lectures. So whenever you will have initial slope, positive slope plus 20 dB per decade, that is due to 1 0 at origin. So 1 upon s will be there, one term will be there. And now at this point, at this corner frequency, there is a change in slope. So earlier slope was plus 20, now it is becoming 0 dB slope. That means minus 20 dB per decade is a change. And so this minus 20 dB per decade, this change is due to one pole, because one pole can provide minus 20 dB per decade. So there is one pole. So you can see that there is 1 0 at origin, right? Because s term will be there, only s in numerator, not in denominator. Okay, this is a plus 20 dB per decade. So 1 0 I can put it here at origin, s. So it is k times, k could be anything, okay, on constant, k times s. And here I have one pole because it should provide minus 20 dB per decade. And then again there is one bending here at b, and here there is change in slope is minus 40 dB per decade. So that is minus 40 dB is 2 times of minus 20, double of minus 20 dB per decade. Thus we should have two poles at this corner point. Means I should have this function 1 plus s by b, that square, and for this one I have this function 1 plus s upon a, one pole at s equals to minus a, and here I have two poles at s equal to minus b. So that's how we have square here. So this plot should have this kind of GS: 1 0 at origin, one pole at s equal to minus a, and two poles at the same place s equal to minus b. Now you can see the options given. Obviously this is not true, because A should be numerator. B is not true. And C is also not true because quad term is not there. So either A or D could be true. Okay. So which one, A or D, that we need to find out again. So this is the form. So now I try to find out this A and B. Now consider this one, this line, straight line. The slope is given 20 dB per decade. So I assume that this function is y equals to mx plus c in this form. Here x-axis is log of omega, because this omega it is written here, but actually it is log scale. So thus it is log of omega, log base 10. Okay, and 20 is the slope plus 20 per decade. So 20 times log of omega plus some constant c, y equal to mx plus c, that form, linear straight line equations. Okay, so if I assume, and y is obviously in dB scale, that is called in dB scale, right? So from here I'll get two equations, because at this is provided already that at point 5 its value is 0 dB, and at A value is plus 12 dB. This is a point plus 12 dB. Okay, so I can have two equations. So at, if I replace omega equal to A, then y should be 12 dB. So this is your 12. This is 20 log A plus C. And for this 0.5, when omega is 0.5, then it is 0 dB, y equal to 0. So I'll put y equal to 0. And when I replace omega by 0.5, so 20 log 0.5 plus C. So these are two equations I can solve for A and C. Two equations, two unknowns. So see, if I subtract these two, simply I can cancel. So C will be cancelled out. Okay. So that I will do. So it's 12 minus 0. So this minus this, C will cancel. So it will be 20 log A minus 20 log 0.5. So this 12 equals to 20. So this log subtraction I can write in this form, log A by B form. So 20 log base 10 A upon 0.5. Now we can solve for A. Now this is log A upon 0.5 base 10 equals to 12 by 20, that is equals to 0.6. Thus A upon 0.5 equals to 10 to the power 0.6, and that is equals to almost equal to 4. Why it is so? Because one important thing you should remember, that log 2 base 10, log 2 base 10 is always 0.3. Okay, that's how 3 dB is coming. So log 2 base 10 is 3.3. Now then if I consider log 4 base 10, 2 square, so the 2 times of 0.3 will be 0.6. Okay, so 0.3 double is 0.6. That's how 2 square is 4. So this 10 to the power 0.6 equal to 4, that you should remember this value. 10 to the power 0.3 is equal to 2. 10 to the power 0.6 equal to 4. Okay, so A upon 0.5 equals to 4. So A equals to 0.5 times 4 equals to 2. Okay, so A we have got. Now we need to find out B. Okay, we'll try to find out the V as well in the same way, but I can give you some simple tricks to find out these points, corner points here from this slope. Okay, now here I should mention one thing, that the slope, if it is provided that 20 dB per decade, it is same as 6 dB per octave. Okay, in control system Bode plot, sometimes instead of 20 dB per decade, the slope will write 6 dB per octave. Octave means double and decade means 10 times. Meaning is that if frequency is increased by 10 times, then the gap Y level change is 20 dB. That is the meaning of 20 dB per decade. And here, if we increase the frequency by 2 times, from omega to 2 omega, then the gap would be, change would be 6 dB only. It is the same thing. Okay, so 20 dB per decade is same as 6 dB per octave. Right, so we need to discuss this thing more. Suppose this is the slope, that is your 20 dB per decade. Okay, this is a log axis, some level is there, it is fine. At omega 1, this is a, suppose one value is there on dB scale, some dB scale is there here, so at omega 1. Now, if I consider 10 times of omega 1, means from here to here, 10 times increment, okay, then the gap, the change in Y level should be 20 dB. So from here to here, it is 20 dB gap. So if initially it is 5 dB, then it should be 25 dB. If initially is 40 dB, then it should be 60 dB, like that. Okay, so 10 times increment in frequency will imply in dB scale 20 dB improvement, increase. That is the meaning of 20 dB per decade. In one decade, there is an increase of 20 dB. So this is the thing. So this is your one decade, 10 times increment frequency change, and this is your gap 20 dB. And that I can show you here, 20 log base 10, and this by this 10 omega 1 by omega 1, this will cancel. So it is 20 log 10 upon 10 base 10 is 1, so it is 20 dB. Okay, this simple thing, this by this. So same thing we have got earlier. The difference is that frequency by this frequency, the log of that times 20. So the same thing I have done. Now, if I consider an octave, octave means 2 times. From W1, if I go to 2W1, 2 times of that one. So this gap is called 1 octave. Then the magnitude change should be 6 dB. It is same. So the slope is same. Exactly same thing I can use. So if it is 10 times increment, 20 dB improvement in gain. And when frequency is changing by 2 times, then magnitude is increased by 6 dB. It is actually the same rate, same slope. Okay, right. And that I can show here 20 log 2W1 by W1. W1 will cancel, log 2. Already I've said log 2 value is 0.3. So 20 into 0.3 equal to 6 dB. Okay, that's how we'll get 6 dB change. So this is important thing. So 20 dB per decade, same thing as 6 dB per octave. That is the information we are going to use it here. That's the main thing we want to use it. And you see here, this value is given 12 dB. Okay, this final value is given here 12 dB. So the change is 12 dB, and that is the 2 times of 6 dB. Obviously, okay. So 1 6 dB change we will get for 1 octave. Another 6 dB I can get. That means 6 plus 6 is 12. It will become 12 for another octave. Okay, that is the logic. So to get 12 dB change from 0 dB 12 dB, 2 times of 6 dB change. Yes. Okay. So you see this 0.1 to 1. If I go for 2 times 0.1 into 2, 0.5 into 2 equals to 1. So at 1 you should get 6 dB. Again another 1 octave, you will get another 6 dB, means you will get 12 dB. So a point should be another it should be 2, because 1 into 2 equals to 2. It should be 1 octave. 1 to a, it should be 1 octave, means a should be 2. Thus value of a is 2. It's very simple. Okay, so a is 2 here in this way. Similarly, we can find out b with the same logic. Now you consider that minus 40 dB per decade. This minus 40 dB per decade is same as 2 times of 6 dB. This should be minus 12 dB per octave, because plus 20 dB per decade is same as 6 dB per octave. Thus it is minus 40 dB per decade, 2 times here, 2 times here. It's a minus 12 dB per octave. Meaning is that the magnitude is falling by 12 dB in 1 octave. Okay, so magnitude should fall by 12 dB in 1 octave. Now you see this magnitude is 12 dB and here it is 0 dB. So obviously this gap is 12 dB. So this 12 dB change we should get for 1 octave. So this gap B to 8, it should be 1 octave. So B should be half of 8, because 2B should be 8. No, 1 octave from B to 8, 1 octave means 8 should be double of this frequency B. So 8 equals to 2B, means B is half of 8, means 4. So B equal to 4. So this corner frequency is 4. I think it is clear. So this corner frequency is 2, this corner frequency is 4. So now I can replace this one S by 2 and this is S by 4. S by, remember, it is S by 2, not S into 2. S by 2. So it is 0.5 S. This thing, and this is S by 4 means 0.25 S. This one. So first A option is correct. Though K we have not yet solved. We have not find out. Okay. We can find out K value of the K. But without finding K value, easily we can choose A. Because this is the only correct answer. This is not correct. Okay, but let us complete this problem. Try to find out the K value as well. Okay, so from here only we can get the solution. The A option is correct. Right, now let us find the value of K. So for this one, I replace A equal to 2 and B equal to 4. And now we are interested to find out the K value again. Okay, so for this I can use one information, any one. So I can try to consider one information which is given very toward the left side of W initially. That means for low value of W. So when W equal to 0.5, its value is given 0 dB. So this is most easy one to use. So at this frequency, or when omega equal to 0.5, that time its magnitude is given 0 dB. This one, that we can use it. And now I have discussed this problem in the last lecture. I have said that at this frequency you need to find out which poles on zeros will contribute at this frequency asymptotically. Okay, so as it is having 1 0 at origin, that will contribute always, because I have said that 1 0 at origin or a pole at origin, for that we will get exact plot. It is continuous plot, continuously increasing or continuously decreasing. Okay, so it will have certain contribution at this frequency 0.5. But this one, this pole will contribute from here onwards, 2 onwards. So when omega is less than 2, it is having 0 dB contribution. Similarly, this pole again, when omega is less than 4, it will have 0 dB contributions. So we can ignore these two. They are not having any contributions in this magnitude. So I'll have only K into S. That's all. These two, K and S. Okay. So GS I can consider as K into S for this time to find out this K value. Remember, just our objective is to find out the K value. Now we'll remove these two. I'll consider one gain function GS equal to K into S, and then I'll find out magnitude G of J omega. G of J omega, so S is replaced by J omega, so K into J into omega. Its magnitude is K omega, and at omega equal to 0.5, it is K into 0.5. Okay, so this is the magnitude. So I need to consider in dB scale. dB is 20 log of magnitude. So 20 log of K into 0.5 base 10. Okay, this is in dB scale, that is given as 0 dB. We need to solve it. Okay, so log x equal to 0 means here it should be log 1, x equal to 1. Log 1 is always 0. Okay, because this should be equal to 10 to the power 0 means 1. So k into 0.5, that value should be 1, and so k equals to 1 upon 0.5, that is equals to 2. So k is 2. Thus this is exactly correct. This k is also fine. Okay, so everything we have got for this problem. So this is your 2s upon 1 plus 0.5s multiplied by 1 plus 0.25s, that's square. Okay, answer A is correct. Now we'll move to the next problem. Now this is a problem. Now this looks really complicated. Now this figure is given, the approximate plot, Bode plot is given for one function gs, and here in gs some values are provided, some are not provided. It is given in this of this form: gs equals to k times 1 plus 0.5s times 1 plus a into s, a is not provided, upon s into 1 plus s upon 8 times 1 plus b into s, b is not provided, and here 1 plus s upon 36. So k, a and b, these three are unknown, but slopes are given in the figure. It is said that minus 6 dB per octave, that we know. It is same as minus 20 dB per decade. It is fine. Now we need to find out this value a upon bk. That means if I can find out a, b, k, these three values, then we can compute this ratio. So how to find these three values a, b and k? So you understand that a we can find out considering one corner frequency. Similarly b also based on the corner frequencies, but k is a DC gain. Okay, so first we will go for a and b. So look at this figure now. So there is one initial slope. Okay, the initial slope, it is decreasing slope, minus 6 dB per octave. That implies that there is one pole at origin. So that is shown here. One pole at origin means denominator you will have one s, some k upon s. Already I have got it. Okay, right. So this 1 upon s we are getting for these things. G of s equals to k upon s. We'll get the full gs. We'll start from left side. We'll go to the right side. So we'll start from here. There's initial slope. Based on initial slope, we have concluded that there should be one pole at origin, this s function, and it can have some DC gain key. Okay. Now consider this point. This is one cross point, corner frequency. Okay, there from here there's one change in slope. So earlier it was minus 6 dB per decade, sorry octave. Now it is 0 dB per octave. So what is the change? Plus 6 dB per octave is increased or added. That's how it is made 0. Okay, so plus 6 dB per octave, that is provided by one 0 only. Only 0 can provide positive slope. So there should be one positive slope at this frequency. Okay, that means I should have one part in numerator, and that corner frequency is 2. So it is 1 plus s by 2. Okay, that one plus s by 2. That is same as 1 plus 0.5s. Okay, this is 0.5. So this is fine. It is given. Then this force. Again, it is increasing. From 0 dB, it is now getting 6 dB. So 6 dB more. Positive slope means one more 0. So there is one more 0 at this corner frequency. So I can write 1 plus s upon 4. Now it is reduced. And whenever there is a reduction in the slope, that is due to the pole. And whenever there is an increment in the slope, that is due to 0. That's simple logic. Okay, and if it is changes by 6 dB, then only one pole at 0, and if it is changed by 12 dB, then two poles at the same place or two zeros at the same place, depending on the sign. So here it is 1 plus s by 4. Right, now it is becoming 0 dB, means reduced. Earlier it was 6 dB per octave slope, now it is reduced, so reduction is due to pole, so there should be one pole at 8. Okay, it implies it is this function 1 plus s upon 8. Similarly, it is also reduced by minus 6 dB from this 24, so there should be one pole. Okay, thus it is 1 plus s upon 24. Now in this figure you see it is not mentioned b, so b should be 1 upon 24. It is missing. Earlier a is 1 upon 4, that is also missing, so I have got this two. So now the last one, there's one more corner point 36, so another decrement 6 dB, so there is one more pole, so it will be 1 plus s upon 36. Okay, so now easily we have got a and b. So what is a? A is 1 upon 4 and b is 1 upon 24, right? But still now we don't know what is the value for k. So how to find the k value? To find the k value, you need to have certain informations. Okay, here which information? So you see, nowhere in y-axis is given except 0 dB. But 0 dB is not corresponding to any corner point, anything. It's not mentioned. Okay, that's why it is challenging. So how to find k value? Right? So this is the one difficulty. Now what strategy can you try for this one? Can you find the k value? Right? Okay. Now I'll let you know how to use these things. Now you see here, this slope is voided. It's minus 6 dB per octave, and it is extended here, and it is showing that it will cross at this point. Means at 8 it is 0 dB, and this is the slope provided. Now we know that this is your minus 6 dB per octave, means every octave, every 2 times of frequencies 6 dB is reduced. Okay, so if we start from here, 8 to 4, this is one octave, because 4 times of 2, 4 into 2 is 8. Okay, so this is one octave. In one octave there should be one 6 dB change. So if it is 0 dB, it should be 6 dB. So at this point this value should be 6 dB, right? That's true, because this is one octave, thus the gap should be 6 dB. Now again, this is one more octave, 4 to 2, another 6 dB. So 6 plus 6, it should be 12 dB. That means at this point its value should be 12 dB. Now you see at 2, omega equal to 2, this is the corner frequency, that times that at that point the magnitude is 12 dB. That now we can use it. Okay, so I can say that at omega equal to 2, the gain is 12 dB for this plot. Now we can proceed the same way. So now we need to understand at this corner point who will contribute. So there are several functions, poles and zeros, and constant. So constant k will always contribute, and pole at 0 will always contribute. But this 0 will contribute from here onwards, but at this corner point its contribution is also 0. Okay, this will not contribute. Again, the 4 obviously it is not contribute. All higher corner frequencies, they will not contribute. Okay, so at this point only the s and k, these two will contribute. Okay, thus I can write 20 log k, and s is j omega, increased by j omega, and magnitude is k by omega, and omega equal to 2, thus it is k by 2 only. 20 log of k by 2 is 12, right? So similarly, you know that 12 means 20 log 4 that I have said, because 20 log 2 is 6 dB, 20 log 4 is 12 dB. So that also we can compare. So this should be equal to 4, k by 2 equals to 4. So k equals to 8. Okay, so I have got A, B and K. Now easily we can find out this ratio, this value A upon BK. So A upon BK, if you replace A, B and K, we will get 0.75. So this is the answer, right? I hope you have understood this problem. So if you have any confusion, now we'll consider the next problem. The problem number 3, this one. So this is the figure given, and for this one, it is very simple figure. It is 0 dB, then there is a slope plus 20 dB per decade, then again it is flat 0 dB per decade from 1, omega equal to 1. Okay, but problem is here is we need to find out maximum phase angle phi m and corresponding gain Gm. This is a different problem from the Bode plot. We need to find out maximum phase provided by the system transfer function. Okay, and that corresponding gain that time. Okay, so how first we need to find out the G of S, and then only we'll be able to find out the phase and the magnitude. Okay, and the transfer function easily you can find out. No, what is the G of S? Because there is a slope from here. Initially it is 0 dB, means there is no poles and zeros at origin. Just there is a corner point here, 1 upon 3. From there it is a slope of plus 20 dB per decade, means there is a 0. So at this, so 1 plus s upon that corner frequency 1 upon 3. And from here there is a change, at 1 there is a change, and it is becoming 0 dB per decade, means minus 20 dB per decade is added from with this plus 20 dB per decade. That's how it is becoming 0 dB. So that it is reduced. So I have said that whenever slope is reduced, that is due to one pole. So there should be a pole at this point. So it will be 1 plus s upon a. Here a is corner point is 1. And there is no k because this level is 0 dB. Okay, its level is not shifted. If there is no shift in this level, then obviously k equal to 1. Nothing is there, no change is there, no DC gain. Okay, so I will not consider k equal to already 1. So if I simplify this one, I will get 1 plus 3s upon 1 plus s, right? Now for this one, if I replace this by j omega, I will get g of j omega. So this is 1 plus j3 omega upon 1 plus j omega. So phase is tan inverse 3 omega numerator, tan inverse y by x. So 3 omega by 1 is 3 omega, minus, due to pole it is negative sign, tan inverse omega by 1 means tan inverse omega. And magnitude is square root of, magnitude of this one is square root of 1 square plus 3 omega square. 1 square is 1 and 3 omega square is 9 omega square. And for this one, magnitude is square root 1 plus omega square. Okay, so this phase we should maximize. So we should understand when this phase will become maximum. For maximum or minimum, so one general procedure is we will differentiate this function phi with respect to omega, then we will make it 0. Okay, same thing we'll do. So d phi d omega will compute. So what d phi d omega? Tan inverse 3 omega derivative is 1 upon, so tan inverse x is 1 upon 1 plus x square. So it is 1 upon 1 plus 3 omega square means 9 omega square. And again derivative of 3 omega is 3. That's how its 3 is coming. Okay. Minus tan inverse omega is 1 upon 1 plus omega square. That's simple. Now, for maximum phase, I'll put it equal to 0. Then we'll solve it. So that means this is equal to this one. 3 by 9 plus omega square equals to, at omega m, it is maximum, I'll consider. So this is the equation and we need to solve it. So if we simplify it, we'll get this one. Then omega, we are getting 1 upon square root 3. That is very simple. Okay, so omega m is equals to 1 upon square root 3. So at that frequency, the phase is maximum. So I can put omega equals to 1 upon square root 3. I'll get the maximum phase. And that time, again, I'll put the omega equal to 1 upon 3, square root 3. I'll get the corresponding magnitude. Now this thing is very simple. So maximum phase is now tan inverse 3 into omega. Omega is 1 upon square root 3. So 3 by square root 3 minus tan inverse 1 upon square root 3. So this is your square root 3. Okay, and tan inverse 1 upon square root 3. Tan inverse square root 3 is 60 degree and this is your 30 degree. So 60 minus 30 is 30 degree. Positive. Remember, this is positive. So in numerator it's 0 and this is pole. Whenever 0 is close to origin, then it's a lead compensator. The phase is provided, positive phase is provided. That will be discussed after few lectures. Okay, we'll be considering compensator, lead compensator, lag lead compensator, everything. Okay, so one thing I can say from here, this is on lead compensator, the phase is positive, and maximum phase it will provide 30 degree, and that is at frequency omega equal to 1 upon square root 3. Right. Next one, the gain. Gain easily we can find out. We can replace omega m equals to 1 upon square root 3. So omega squared equal to 1 upon 3 I can put. So it is 1 plus 9 by 3. Here it's square root 1 plus 1 by 3. If you simplify it, it is becoming square root 3. Now this is square root 3. This is normal. It is not dB scale. But values are, be careful, values are given in dB scale. So need to convert it in dB scale. 20 log of square root 3 means 10 log of 3, and 10 log of 3 is this one, 4.77 dB. Okay, so don't choose these things because root 3 is 1.73, it's fine, but that is not in dB scale. We need to consider in dB scale, so we'll get this result. C is correct answer. Okay, be careful. Okay, next we'll consider this problem. Again, one figure is provided, and this figure looks very simple. There is one slope, downward slope, initial downward slope, minus 40 dB per decade. Then it is becoming minus 60 dB per decade from 2. Then at 5 again it is becoming minus 40. Then again at 25 it is becoming minus 60. I think it is very simple problem. Now can I ask this problem to solve you? So try to solve this problem and share your answer in the comment section. I hope you will be able to do these things and how quickly you can solve this problem. Okay, please share in the comment section, and whether you're still now comfortable to solve this problem or not. Please share these things. Okay, we'll move to next problem, problem number 5. Okay, so please share. Let me know you are getting the right concept or not. The problem number 5. One gain function g of s is provided. This form n0 upon s square plus d2s square s cube plus d2s square plus d1s plus d0. So the third order polynomial in denominator means 3 poles are there, no zeros. So whenever there are 3 poles, so obviously at the end you will get minus 60 dB per decade slope in Bode plot, because each pole will contribute minus 20 dB. So at the end you should get minus 60 dB per decade, and the phase should be, each pole should provide at the end, means that when omega is very large, it should provide minus 90 degree. Okay, so 3 poles means 3 into 90 means minus 270 degree. Okay, and figures are mentioned here. You see the Bode plots are provided, and you can see that the phase plot is moving towards minus 27 degree. Is matching, and this final slope, it should be minus 60 dB per decade. Okay, but this figure is not given because exact pole locations are not mentioned, so we can't comment here like this. But anyway, the question is different for this one. Now here we can put one constant k here in this closed loop function, and then we need to find out for what maximum value of k this system will remain stable. Okay, consider the negative unity feedback configuration with the gain k in the forward path. This one, the closed loop path should be stable for k less than k naught. So that maximum value of k naught we need to find out. Now here you can check one thing. When phase is minus 180 degree, that time magnitude is provided plus 20 dB. So from here we can conclude certain things. So what is that? So you see, so this is 0 dB line. So this gap is 20 dB is provided. Now, when angle is minus 180 degree for certain frequency, that is called phase crossover frequency, and that time the give gain absolute value is less than 1 or less than 0 dB, then only system is stable. Okay, so at phase crossover frequency, if actual gain is less than 1 or less than 0 dB, some negative dB, then only it is stable. Otherwise it is unstable. So you see, in open loop system it is already unstable, because at minus 180 degree it is plus 20 dB. So it is already unstable. We can make it stable under closed loop systems. Okay, so with meaning is that with k equal to 1 it is unstable, right? With k equal to 1, so obviously the maximum value k should be less than 1. That is sure, right? So maximum value of k naught should be less than 1, because this one. Now when it will be marginally stable? So marginally stable you will get when it is gs equals to minus 180 degree and gain is also 0 dB or 1, magnitude 1 or 0 dB. Means this plot, if I reduce scale down, it's upward or downward. So this is, it is lifted up or it is down. It is because of the DC gain k. If k is more than 1, okay, then it is increased, shifted up, and if k is less than 1, then it is shifted down. Okay, so for marginal stability, this point should be at 0 place, because at minus 180 degree, that time gain should be 0 dB line. So this gap should be 20 dB, right? So using k only we can reduce the level. So 20 log k is your change in dB scale. That should be 20 dB, but negative, reduce, it should reduce. So in other words, I can say that 20 log k naught should be minus 20. Be careful here, it is reduced. So we need to choose k naught in such a way that 20 log k naught, it should provide minus 20. Then from plus 20, minus 20 is added, it will become 0 dB. Okay, so 20 log k naught base 10 should be minus 20 dB. Now we can solve for k naught. So log k naught upon 10 equals to minus 1. So k naught equals to 10 to the power minus 1, means 1 upon 10 equals to 0.1. Okay, so this is the idea. So from here you can get some idea about the stability using the Bode plot. In Bode plot, if at phase course or frequency the gain is provided positive, it is unstable. We can make it stable by decreasing the gain. So k value should be reduced less than 1 in this way. And here you see with k equals to 0.1, it is coming to marginal stability. And when k is less than 0.1, it will become stable. Okay. And suppose by k equal to 0.01, then what will happen? It is reduced by another 20 dB. It will come at minus 20 dB. That time gain margin will be 20 dB. Okay, it is good. Anyway, we'll discuss gain margin, phase margin in different lectures. Keep watching. I'll be discussing many other problems in next videos. So if you enjoyed this video and if you have not subscribed yet, you may subscribe it. I'll be discussing more problems. Okay, it could be useful to you, and you can like this. If you enjoyed this video, you can press the like button. It is helpful for me. Okay, please encourage me by pressing the like button. Okay, thanks for watching. We'll meet in the next video.